The Earth has undergone dramatic change over its geologic history. As the Earth has cooled and warmed, ice fields have advanced and receded. During warming periods, ice melts and water expands, causing sea level rise. Scientists are studying how sea level rise may affect coastal wetlands. A key study site is the Mississippi River Delta, which is experiencing high rates of relative sea level rise due to rapid land subsidence. Subsidence is the process of sinking to a lower level. Sediment deposited by the river undergoes subsidence due to compaction and dewatering. As water and gases are squeezed out of spaces between soil particles, soft sediment compacts. As the sediment compacts, subsidence occurs and the land gradually sinks. Buildings and other structures also sink along with the soil surface. The other process contributing to land loss is sea level rise. As global temperatures rise and land-based ice melts, oceans expand. As ocean volume expands, sea level rises globally. This is known as eustatic sea level rise. Relative sea level rise is the combination of eustatic rise in sea level and land movement, and is unique for each location. The combination of the two processes determines the rate of submergence in each coastal area. The Louisiana coast is a dynamic system, built in part by the action of the Mississippi River. To understand how subsidence affects the Mississippi River Delta and its wetlands, we first have to go back a few thousand years. Because glaciers were melting 8,000 years ago, sea levels were higher at that time, so much of the present-day coast was underwater. Where New Orleans is located today was also under the sea. Sea level continued rising, forming a bay that would ultimately become Lake Pontchartrain. Sea level rise then slowed, and the river began building up sediments along the coast. Scientists call these deposits delta lobes. Additional delta lobes were formed as the river switched from east to west and back again. When the river switched to a new course, the abandoned lobe began to deteriorate, a process that caused formation of barrier islands. The last area to form is what is now the modern delta. This cycle of land building, followed by deterioration and rebuilding, is a natural part of the delta cycle, which has created a vast expanse of marshes, swamps, and barrier islands. The river periodically overflowed its banks each spring, delivering sediments to the coastal marshes and swamps. Then Europeans arrived on the scene and established New Orleans in a bend of the Mississippi River. To prevent flooding of New Orleans, levees were built, and these were extended as the city grew. Then in the 1920s, there were catastrophic floods such as the Great Flood of 1927. Disastrous flooding prompted the construction of levees, which eventually extended the entire length of the lower part of the river. Levees prevented natural sediment delivery to the wetlands in the delta. Instead, sediment was shunted offshore into deep water, and the wetlands sitting atop compacting sediment began deteriorating. Scientists attribute a portion of wetland loss to direct and indirect effects of canals, which were built for navigation as well as for access to oil and gas wells. Material was dredged from the wetland and deposited in spoil banks along the canals. These spoil banks acted like levees, blocking natural tides and currents, and generally altered the hydrology, increasing the depth and duration of flooding. Wetland plants must tolerate periodic flooding. When a plant establishes in a well-drained soil, the pore spaces between soil particles are filled with oxygen. Upon flooding, however, soil pores become filled with water, and respiration of microorganisms uses up oxygen faster than it can be replaced. Thus, flooded soils have little or no oxygen. Plants tolerate such low oxygen conditions by developing special airspace tissue inside the roots called aerenchyma, which creates an internal aeration pathway that allows oxygen in the atmosphere to reach the roots. This is one mechanism that allows plants to survive flooding. Although wetland plants are adapted for growth in flooded soils, excessive flooding causes stress and lowered productivity. Over time, the vegetation thins and dies out, leaving ponds that coalesce, forming open water behind the spoil banks, which ultimately subside and disappear. Storms and hurricanes can also damage wetlands, causing shoreline erosion, burial with wrack, which smothers vegetation, and other impacts. However, hurricanes may also deliver nourishing sediment that counterbalances subsidence. Hurricane Katrina, for example, delivered several centimeters of sediment to coastal marshes, raising soil elevations and reinvigorating marshes. Evidence of sedimentation from prehistoric hurricanes can be seen in cores collected from coastal marshes, indicating that storm sediments have also contributed to accretion in the past. Rising sea level can also bring salt water farther inland. A common misconception, however, is that all wetland plants are harmed by salt water. In fact, several coastal plant species are tolerant of sea-strength salinity due to special morphological and physiological adaptations. For example, the extensive salt marshes in the coastal zone are dominated by a plant which grows well in salt water called smooth cordgrass. Another species common to the coastal fringe is the black mangrove. These species have salt glands in their leaves, which excrete salts onto the leaf surface where they crystallize. This is just one of several special mechanisms allowing such species, known as halophytes, to thrive in salt water. Other species common to coastal marshes have lower tolerances of salt water. These are found in intermediate and brackish habitats, where they grow well under low to moderate salinity levels. The most sensitive plants are found in freshwater wetlands. The species here can be killed by sudden pulses of salt water. However, depending on the duration of exposure and other factors, the community may recover from seeds contained in the seed bank. The causes of wetland loss are complex and not the result of a single factor. Instead, wetland loss is the consequence of multiple interacting natural and human-induced factors, such as subsidence associated with the deltaic cycle and the leveeing of the Mississippi River, in combination with regional and global changes such as sea level rise and climate change. One thing is certain: the Mississippi River Delta is a dynamic system that has undergone dramatic changes over its geologic history and will likely continue to change in the future.